Hello everyone, so we are going to build an event parity checker in Proteus simulation software. Alright, so in our previous tutorial we have actually built event parity generator in Proteus simulation software. So if you don't know how to build it, please go through my previous tutorial. So right now we're going to build an event parity checker circuit. Alright, so the circuit diagram is right here. So the circuit diagram is quite easy, so I'm just gonna build it right now. So uh, before building that, so let me just run the simulation of event parity generator once again. So at the very last we actually gave the input 1110. So there were 3 ones in the input since this was an odd number. So and we're working with an event parity generator, so to make the number even, the output has produced a value of 1. All right, so there were 3 ones, odd number of ones, so the output produced a value of 1. Alright, so let's build the event parity checker right now. So the event parity checker is actually a part of event parity generator. So I want to build that whole circuit again. So let me just build it quickly. Alright, so I have actually built almost the larger part of this event parity generator circuit here. So I did not complete the circuit because I will be adding some new components to this circuit, because it's not actually the same circuit. It's like this circuit, but it's not actually the same as this circuit. So I want to build an event parity checker. So what I need to do is I want to add another input here, another logic state. All right, and I want to use another XOR gate. So as you see, there were 4 XOR gates, so I want to use another XOR gates. So I want to use it right there. Okay, so now I'm just gonna complete the circuit. So this part right here is actually the part of event parity generator. So the output of that part is going into another XOR gate, and here is another external input, I should say. So this input is directly going to this XOR gate 2, and the output from this XOR gate goes to the LED light. Alright, so now our event parity checker circuit is actually complete. So let's check it now how it works. So in case of event parity generator, we saw that for input 1110 we actually got 1 at the output, right? When we ran the simulation, we saw that for input 1110 we got 1 at the output. All right, so if we give the same input here, 1110, so we should be getting 1 at the output right there, where I'm showing where I'm moving my cursor right now. So right there we should be getting 1 at the output. All right, so let's consider it like this. So we're actually sending this bit pattern 1110 to the receiver. All right, so we are actually sending the same values of 1110 to the receiver. So we want to check whether we can actually send the correct data or not. We actually want to check whether the correct data reaches the receiver or not. So that's why at first we built a event parity generator, and the parity bit was 1 at the output. So right now we are actually sending these whole 5 bits to the all of those 5 bits to the receiver. So actual 4 bits of the data 1110, and since the parity was 1, so we want to send 1 as an external input to this circuit. All right, so we're sending the actual bit patterns 1110, and we are also sending another 1 since the parity generated from the actual bit patterns was actually 1. So we are sending this one to we're appending to the original circuit. All right, so we're sending these 5 numbers. All right, so what actually is happening here, here from this part 1110, the output will be getting right here will be 1. All right, so this 1 goes to this XOR, and another 1 is coming to this XOR. So if the XOR gate has two inputs and both the inputs are 1, so at the output it should produce 0. So let's check whether it produces 0 or not. So I'm going to run the circuit here. So yeah, right there the LED is not working, so the output is 0. And as you see from this circuit diagram, if we get 0 at the output, that means no error. So what does it mean by this information? 0 no error and 1 is error. So you can see the actual data we wanted to send is actually 1110, right? We sent this data and we actually checked the parity bit by running it through the parity bit generator, and the parity bit is 1, and now we are actually sending this 1 to this parity bit checker circuit 2 along with the data. All right, and since the data was not changed, so at the output it is actually producing 0. So from this part the actual parity bit is generated and it is 1, since we are doing an even parity. So this one is getting XORed with this one, and as a result it is producing 0 at the final output. That's why it is saying that there is no error because the data was not changed. But let's say somehow your data was changed. Let's say somehow instead of 1110, you are sending or you are getting at the receiver like 1010. All right, so you can see that the data we intended to send was 1110, but we're actually sending the data, or the data was somehow corrupted and the data sent to the receiver was 1010. All right, so as a result, since there is 1010, so at this part right here you will be getting 0 at the output because there was already even number of ones at the data, so you'll be getting 0 at the output. So if you get 0 at the output, then this 0 will be going here at one input of the XOR gate, and the 1 is coming to the XOR gate right there, so you will be getting 1 at the output because 0 and 1 produces because if you enter 0 and 1 in an XOR gate, then the output will be 1, so you'll be getting this LED light as working, right? So that's why the output is 1, and if we get output as 1, then it will say that there are some type of error in this data, because we did not want to put this data to the receiver. We wanted to send this data 1110, but here we can see that the data is actually 1010, so there is definitely some type of error, and the circuit actually proves that there is some type of error. All right, so the procedure is actually, so whenever we want to send the data, at first we need to run it through the parity bit generator, and the generator will generate a parity bit, and then we want suppose if the data gets changed at the middle of the transmission, since the receiver already knows the parity bit, we'll be sending all of those 5 numbers to the receiver, so the receiver already knows the actual parity bit, but somehow the data got changed of the transmission, so that's why the circuit was able to identify that there was a mistake. All right, so in this case the circuit was able to identify that there was a mistake, so it produces a 1 at the output, so it says that there is an error. All right, so this is how an even parity checker works. However, there is a very important part right here. So as you see, we have only changed 1 bit of our actual input data, right? The input was 1110, and we changed only the second bit from the top to 0 from 1. So we have actually just changed only 1 bit. So since we changed only 1 bit, so at the output we are getting 1, and we can know that yeah, there is an error. But what if we change another bit? All right, so let's say we change this bit too right now. Okay, so right now the data is actually 1011, but we did not want to send this data, right? We wanted to send this one 1110, but somehow data got corrupted when it data got corrupted at the mid path, and it got changed to 1011. All right, but still the output is producing 0. So we learned that 0 means no error, right? So as you see, the output is producing 0 here, so there should be no error, right? But you can see clearly that the data being sent here is actually not the original data. but why is it producing 0 here? So you can see right there that the input data is original input data was 1110, but we're actually sending 1011. So for 1011, at this part we will be getting actually 1 at the output. All right, we will be getting 1 at the output because there were odd number of ones in the input. So this one will be XORed with this one here, and it will produce 0 at the output. So it will eventually say that there is no error, but there is actually an error. So basically what I'm trying to say is that by using even parity checker, you can only catch single bit error. You cannot catch more than 1 bit error. So 2 bit errors or 3 bit errors, you cannot actually get a hold of them by using even parity checker. There are some other ways to catch double bit errors or triple bit errors, but by using even parity checker, you can only catch single bit errors.